Okay, so we'll get going. My name's Adrian Jackson, and I'm giving the lecture this afternoon and helping you out with the practicals. So, welcome. I appreciate you may not have had a lot of time at the moment, a lot of time so far, to do the practical that you started before lunch. Mark tells me that the lecture went on a bit longer than expected or planned. So you maybe haven't quite got to the bottom of that practical, but that's fine because I've got a lecture now, and then after that the rest of the afternoon is free to do the practical that was before the break, before lunch, and another practical as well. So there's another practical looking at compiler and compiler optimization. So there is plenty of time built in this afternoon to do that. If you have any questions as we're going along, then please do feel free to jump in and ask them. Either I'll try and keep an eye on the chat window, but also feel free to unmute and speak to me as well. All of those are welcome options. So what we're going to talk about now is one of the main tools you have for doing performance optimization of compiled codes. So not all applications you may develop may be compiled, but a lot of the high performance applications will be. They'll be in languages like C and C++ and Fortran. And those are languages where there's a language specification which then gets turned into something that can run on the hardware through a process called compilation. So a process where you take the text that you've written as an application, which is really just a bunch of text documents as your source code, your files, and you run them through a tool which converts that defined software approach, that defined set of functionality into something that can run on the hardware. And that's what the compiler is doing for you. It is possible to use computers without compilers. And there's two ways to do this. One is you use a language that is not compiled, it's just interpreted like Python or Java can be, where you write the language and then you run another program which reads your program and runs it dynamically, so it runs it instantaneously for you rather than creating something that you can run in the future. And that can be that sort of interpreted language can be quite an easy and nice way of doing things, but it doesn't tend to get as high performance as compiled languages because you have all the you have the interpreter taking up resources on the node, which reduces the resources that your program can use. You can also write instructions or assembly code, which effectively directly create the things that will run on the processor, on the hardware, on the computer. But the problem with that, of course, is it's very low level and quite hard to do and not portable. So you can write a whole program in assembler, but then if you wanted to move that program onto another processor or another piece of hardware, then you wouldn't easily be able to do that. So we have this idea of compilers instead, so we can write programs in a higher level language like a C or a C++, and there we have access to much more useful and general programming constructs, so I can easily construct my program to do the things I want to do rather than having to work down at the instruction level. And the added benefit of that is we can also build these clever tools called compilers, which will try and make your program as efficient as possible on the hardware you're using. So compilers do this manual process of taking code and turning it into instructions, but on the way they can apply a bunch of optimizations to make those instructions as efficient as possible or as efficient as they can. And so optimizing compilers are a great thing for us because we can write our programs in something we understand and then turn it into something that runs efficiently using these tools. Now, compilers are not single monolithic things that do the same thing all the time. They're very configurable, and they're designed to do lots of different tasks. And in fact, when you use a compiler, you can modify what it does. You can tune what the compiler does by using what we call a compiler flag, which is really just little arguments that you give to the compiler when you run it. And so compilers typically have very large numbers of flags which control how they produce code, what optimizations they do, what error checking and standards, language standards they apply, and all those kind of things. They also generally have some utility flags which help you put together a lot of these other flags into common groups to make it easy for you to do some things on it. So the example we've got on the slides here is optimization level. So here you can see it says minus capital O1 or minus capital O2 or minus capital O3. And most compilers for languages we will use have things like this, which specify an optimization level. So optimization level 1 will turn on some of the optimizations the compiler do, but not all of them. Optimization 3 will turn on a lot more, and there's some control you have over those to help with the balance between performance, correctness, and functionality. This is because some of the things that the compiler can do and will do to optimize codes can actually change the results of your code. So particularly with floating point numbers, so adding numbers like 1.5 added to 2.7, that's always going to give you the same answer. It should always give you the same answer. But when you get to 1.5973, something that's got a lot of digits on it, the hardware, the order that instructions are done on numbers like that can change the result you have, because computer hardware is of a limited precision. So we may be using 32-bit data types or 64-bit data types, and they can represent a certain level of precision. But where you're doing numerical operations on those floating point numbers, you have to have some rounding in there, because you can't exactly represent all the numbers. You can only represent a subset of them, depending on what numerical precision you have. Because of this, the order that you do calculations can slightly change the results you get for some applications, for some approaches, for some algorithms. And when you turn on things like optimization level 3, the compiler might do more aggressive, for instance, reordering of your instructions and reordering of your code, as long as it's still correct in the sense that the dependencies specified in your code are maintained. It has more scope to do that. So, cut a long story short, compilers, when you're developing your code, when you're writing new code, it's often good practice not to have compiler optimization turned on. So turn optimization level 0, so minus capital O 0, just to make sure that whilst you're developing and testing the code, you've got a good handle on the correctness of your results. You're not having results that are being modified by the compiler and its optimizations. You can always also turn on helpful features in the compiler whilst you're developing your code, which will help with debugging problems, checking that you're doing the correct thing, and doing profiling, so looking at the performance of the code. So that's what you're doing. And then once you're happy you've got a correct code, it's producing the results you expect, and you can verify that, then you would turn on these optimization levels and look at what performance benefits that gets you, and make sure your code is still producing correct results. Likely you want to have some test cases and some tests set up so that you can run your code and check that it's producing the correct results. And as I say, you can try out these different optimization levels the compiler gives you whilst keeping an eye on correctness, because some of the More aggressive optimizations, optimization level 3 and above, may break some people's codes, may produce incorrect results in their codes. Now you can often find out, you can definitely find out what the compiler will do by reading the compiler documentation. And so compiler documentation will list all the flags that are available. And actually, I've not done it yet, but let me just log into ARCHER2 and have a look at what the compiler document. I'll just sort of show you what the compiler documentation looks like. So give me a second whilst I log in. Just need to grab my phone so I can do my multi-factor authentication. And whilst I'm doing this, if anybody's got any questions, do feel free to ask. But I'll just put it in my multi-factor authentication code. Okay. Let's go. Change these settings so it's visible. What the screen is relatively readable, so you can see it. And then I'll share the screen for you. Stop sharing that one. Share this one. So this is me logged into ARCHER2 just as you come in, and you should be aware that there are different different compilers you can use. So if I have a look at what I've got loaded at the moment, I've got the Cray compilers loaded at the moment for this program environment here. And so if I do a man Cray CC, so that's the Cray compiler, then you get up this page which tells you all about the compiler. And you can see that there are all these compiler flags, which are different arguments to tell it to do different things. This one up here, minus FPP equals level, selects a level for Cray floating point math optimizations and the maths library functions. Requesting the lowest level, minus FPP equals 0, will generate code with the highest precision and grants a compiler minimal freedom to optimize, whereas requesting higher levels will grant the compiler maximal freedom to aggressively optimize, but will likely result in lower precision. And so there's all sorts, as you can see in here, all sorts of different options. Not all of this is about optimization. Some of it's about language standards. Some of it's about interoperability with other programs. Some of it's about debugging. But here you can see there's code generation options O0, 1, 2, 3, fast, OS, OZ, OG, O4. And so there's, in the Cray compiler, there's a range of different things you can do. Exactly the same for Fortran. Different documentation, but exactly the same. There's a long list of compiler options that you can use with various things described and how they work. And C++ would be the same. Again, tells you all the things and looks very similar to the C one actually. If I load up the GNU compilers, so instead of Cray CC and Cray FTN, I'm using GCC and GFortran. And then if I type a man GCC, you'll see there's very similar kinds of thing here. Lots of documentation, lots of language options, warning options, debugging and optimization options, developer options. So there's loads of different things you can specify here because the GCC and GFortran compilers are a bit more general, so they can run across lots of different hardware and there will be flags for specific things. And so I could have a look for, say, the optimization level here. And again, you'll see that controls for optimization levels, and it will describe some of the things that you can do on the compiler. And then it will say, you know, optimization 1, this is what this turns on, and optimization level 1, just turns on all these flags here. Now, optimization level 2 will turn on optimization 1 and a whole bunch of extra flags on top of that, and it gives you some warnings about that. And then you can go above that, and you can optimize for size. So optimization S will optimize for the size of the executable you create rather than the speed of a program, or fast and optimization debug. So there's lots of different options there. And exactly the same G4tran. We'll do the same kind of things. Not quite as much stuff there because it doesn't tend to be used across quite as much varying hardware as GCC, as a C compiler. Okay, let me go back to sharing the PowerPoint. So that's what you have. And now you can, sometimes when you're doing heavy optimization, you can sometimes get to a point where your code breaks if you turn on, say, optimization level 3 or 4. But often it won't be all of your code which is having problems with that optimization level. It may just be one function or one set of functions or one file with all the code inside that. And so if you really want to get high performance, you can often go through and specify different optimization levels for different files that you compile. So if you write a program, it's split up and all the functions are in separate files, or groups of functions are in separate files. You can actually specify, well, for all these files over here, use the optimization level 3, but for this one file here, which is causing me problems, use optimization level 2. And this is what the thing at the bottom was here. You can do this idea of a binary chop, where if you turn up optimization, you start getting errors in your results from your program, then you can keep it turned up and take out, drop down the optimization level for individual files or groups of files to see where the problem actually is. And you may still be able to optimize most of the program at a high level whilst maintaining correctness by optimizing some functions or routines or files at a lower level. One of the important things to remember is that the compiler takes your code, turns it into instructions, and when it's doing that, it's turning it into instructions for particular kinds of hardware. And so different processors, like an Intel processor versus an AMD processor versus an ARM processor, may have different instruction sets. And actually, you know, AMD generation 2 processor will have a different set of instructions than a generation 3 processor or a generation 4. So new versions of hardware can have new instructions or modified instructions. Now, there are backwards compatibility in these things. Something compiled on the latest hardware should still the newest hardware should still be able to run old programs on it generally. But you may not get the best performance out of it because you may not be using the most efficient instruction that processor has. So what's important is when the compiler is generating optimizations for your application, when it's converting the code into instructions and optimizing that, it will be taking into account what hardware it's going to run on. So it needs to know the hardware, and often that is done by looking at the hardware that the compiler is currently running on. So if you compile your code on the same hardware as you're going to run your code on, it can generally work out what kind of hardware is available and optimize for the specific hardware you're using. But it can be the case where you have big HPC systems, and it's not the case for ARCHER2, but it has been in the past, where the login nodes where you do your compilation have different hardware in them, different processors than the compute nodes. And then you may want to put in some special compiler flags which says, okay, we're building on this, you know, processor generation 4, but we're going to run on processor generation 5. So optimize the code for processor generation run 5. And again, I'll just stop sharing this and share back the ARCHER2 window. So an example of that is if I did a man GCC, if we have a look at these, not optimization, yeah, machine dependent GCC. Yeah, and so if you have a look, there will be, let me just see if I can go down stage. Here we go. So if we have a look here again, with all these optimization options, there will be ones for different kinds of processes. So all these things down the side here are different instruction sets, different processes. So there's RISC-V options, there's RS6000 options, those kind of things, Spark options, x86 options. And so generally you can specify these things like mtune, march, mcpu, which let you actually specify this is the kind of hardware I want to build for. So if we have a look at march equals, in this example here, for the ARM one, you can specify my march equals and then build for this instruction set. For the, let me go all the way through, because we're not particularly interested in ARM for ARCHER2 because we don't have ARM processors in ARCHER2. Let me see if I can find the x86 ones. And you can see there's lots of, this is why, the general purpose compiler like GCC has lots of different functionality in it. So it can target all these different kinds of processes and it can do it efficiently. So we're all the way down to RISC-V now. But we're not quite at the x86 ones, which is what the ARCHER2 processors are. So even though it's a AMD processor, it's built off this x86 instruction set. And so here you can say, generic x86 instructions, and then you can build for very specific processors like a Pentium, a very old processors now. If you were building for a new Intel processor, you could build for things like Silvermont, and beyond there, or Cannon Lake. And these are all newer Intel processors, Rocket Lake. And you can see what here is it's specifying different additional instruction sets here that it can build for if it knows it's doing that. And you can see that they vary depending on the hardware used. And then there's a whole bunch of the AMD systems as well. So something like ZN-Ver2 will specify code for particular kinds of processors, including the similar ones to the ones we're running at ARCHER2 as well. Now this is all done for you by default because we build it on the same hardware as you're going to run on. So you don't have to do that. You don't have to put any effort into doing that yourself on ARCHER2. But it is the kind of thing that you have to be aware of when using a compiler and when looking at optimizing a program for a particular hardware, particular piece of hardware. The other thing to bear in mind with compiler optimizations is you're not guaranteed that a given flag, even though it's called an optimization flag, will actually make your code go any faster. They tend to just be applying a pattern which for other codes in the past has produced performance benefit. Doesn't mean it will for your code. Now in general, you can expect the optimization level 1 to 2 to 3 there to be some performance benefits. Definitely going from no optimization to optimization level 1 and then optimization level 2, you will get some performance benefits there, but you're not guaranteed beyond that you'll get your code going much faster. You can also put things into your code which the compiler, which are not part of a programming language you're using, so they're not C and they're not Fortran, they're not C++, but they can tell the compiler things, so little directives or additional information which helps the compiler do some things, so optimize some things. Things like values of variables, independence of loop iterations, aliasing properties. There are things where the compiler can find it hard to optimize the code because it's, for instance, I don't know how long this loop is, so I can't do some of the special unrolling optimizations that I could do. But if you as a programmer know, oh, this loop's always going to be divisible by 4, this loop is always going to be, a minimum of X iterations, and you can give that extra information to the compiler, it can help as well. The nice thing about these is they effectively become comments in the code, so they don't affect your portability. So you can do some optimizations in the code which may help the compiler, but if you're using a different compiler or using hardware that doesn't use that particular feature, then it won't affect your porting of code to that kind of thing. I'm not sure if I've got any examples. I don't have any examples here. I'll look out some examples for you. Let me just check there isn't any. Yeah, I will look out some examples of those kind of pre-processing directives because that can be useful to you just see what it looks like as well. But I'll do that later. Apologies. Compilers only can work with the limited information that's available to them. And so what they do is they go through and look at each individual chunk of code and try and optimize it. So effectively they'll take one file, look at the code inside that file and optimize and generate their code on that, and then they'll move on to the next file and then the next file. That's because it's very hard to, particularly for big programs, for the compiler to keep the information of a whole large program in its memory all at once. And so that can also introduce some inefficiency in the optimization it can do. There are ways to help with this and maybe let the compiler do a bit more optimization if you see more code than just a single file. One of the ways is when you write your programs, you can use some options in the language to tell the compiler things. So in Fortran, we can have these things, intent statements, which tell the compiler whether a variable that's an argument to a subroutine is updated inside the routine, or whether we expect data to be copied in or copied out, and that can help the compiler optimize how that variable is used inside the subroutine. And pure is one of these things which says that this function doesn't affect any other functions, so you can optimize it without worrying about any other parts of the code. So you can do maybe more aggressive optimizations there. Const is a C and C++ modifier to variables and functions and the likes, which tells the compiler that this is not going to change or make any changes to the rest of the program. So those can help the compiler do some of the optimizations for you. And then there are also command line flags, which we'll see slightly later, which can specify things like do procedural optimization. So try and look across multiple files to see what's going on. Now the downside of that, I mean, you could ask why don't we do that all the time if that's available. The downside of that is it slows down the compilation, it slows down that process, it makes it more costly. And for a lot of applications, you maybe are not as concerned about performance, particularly outside of using big systems like ARCHER2. So you don't want to be paying that price of looking at all across the program to optimize it. You want your compilation to be quick and efficient. So that's often why it's not done by default. Now, the ideal case is the compiler does all the optimization for you, and you don't have to change your code. And that way you've got a win-win situation. You've got code that you've written which you're happy with and understand, but the compiler is making it fast for you. Of course, there may be times when the compiler struggles to optimize your code for various reasons, but it just doesn't have the information available to do some of the optimizations that you could do by hand. And so you may have to modify code to improve performance as well. Of course, the trade-offs there is you may introduce bugs, you may make the code harder to read or maintain, and you may end up doing optimizations to your code which are not as portable as the general code. So not if don't give you good performance on other architectures. So often when we're doing optimization of a program, what we're looking to do actually is say, well, how can we help the compiler do this rather than be rewriting the code to do the specific low-level optimization that will improve the performance. There can be a lot of, well, the compiler's not doing something here which I think it should optimize it here, so can we rewrite the code to help that out? How do we know what's going on there? Then you're starting to get into more complicated parts of this process. So you can look at the instructions that the compiler produces, so the assembly code, and see whether there are any reasons why that code would be slow. This needs quite a lot of experience, and you can only look at small parts of the code because assembly is very verbose, and so you can't really analyze the whole program like that. But if you're optimizing one particular key function or subroutine of your program, then you may at some point want to have a look at the assembly code that's produced and then try and work out if that is doing sensible things. The easier and more sensible thing to do is to look at the diagnostic information that the compiler can give you. So when it's doing its optimizations, it can tell you what it's done and why it's done it. So you can turn on login output from the compiler to say, oh, I tried to do this thing here, or unroll a loop or vectorize it, but I couldn't because I didn't know if it was safe. And then you can go and have a look at that loop and say, oh, I can see what's going on here. Let me make a change for the compiler to do that more easily or something like that. The other thing you can do is performance modeling. So things like roofline models, which we won't go into any details, but there are ways to profile your code and then work out how efficient it is compared to the overall hardware architecture. So how, what percentage of a peak performance of the architecture you're getting of the hardware, and is that what you're expecting? And so there are modeling and profiling and analysis approaches that can be used to look at the performance and say, okay, I probably need to go in and optimize here because we're not getting the performance out that we would like. What are some of the things that code changes that you can make which can benefit the compiler? Well, there are some pretty straightforward and simple things you can do. So compiler works very well what we call local variables. So variables which are declared inside a function or a subroutine. That is because it understands their lifetime and it understands that no other bit of code is going to be modifying these variables. So it can do a bit more optimization on them because it knows how much you can move them around before it breaks them. So it likes local variables rather than global variables. And so if you can refactor your code to get rid of global variables, so things that are created and defined in one place but used in many places of the program, then that can help the compiler do more optimization. And if in a programming language like C, file scope globals is so this is where you create a variable that's defined outside of a function in a single file, but it's not specified as an external. Now, if you don't do C programming, then none of this will make any sense to you. But basically, it's just a saying, if you can make sure that the way you program and create and use variables very much focuses on using local variables where the definitions are and usage are local to functions or to single files, and that will help the compiler in its optimization job. Conditional code, so things like if statements, can also cause performance issues for your applications. There are inside modern processors, there are functional units, there are quite a lot of infrastructure to try and deal with these if statements and similar kind of conditional statements. Why are they expensive? Well, modern processors really work on this idea of pipelining. That is, they may have 20 instructions that are active at once because a lot of the hardware inside of them takes a number of clock cycles, a number of iterations of the processor to get a result out of them. And so the way that they work is they create a pipeline of instructions so that when one is being worked on, another one can be started. And then when that one's moved on to the next stage, the other instruction has moved on to the next stage. And so you can have multiple instructions active at once. And you can hide some of this overhead of having things take a bit of time to work, because as long as you can start a new instruction every clock cycle, then you can keep that processor full and keep it busy. And this is fine, except if you don't know which instruction to run next. You can't start a new instruction until your current instructions have completely finished. In this if statement down here, let's say this n variable is not known here, it's calculated in the line before, then it's hard for the compiler to be able to run anything after here until that n has been calculated. And that means that n calculation, so the instruction that does the calculation of n, has to flow all the way through the pipeline. You can't start any new instructions. You have what we would call a bubble in the pipeline or a stall in the pipeline. And that means that you're sort of draining down your processor with no effective work being done until you get this instruction finished. And so this is why conditional branches, like ifs, but also things like ends of loops, can introduce inefficiencies in how the processors is used, because they are they give the potential for stalling a pipeline. Now, there is hardware in there which tries to predict branches like these. So there's something called a branch prediction unit, which says, have we seen this branch before? Have we seen this if statement before? If we did, what happened last time? Or maybe what happened the last 2 times or last 3 times? And then make a simple prediction based on that. So things like loops, like this do loop here, which it could be a for loop in C. It doesn't look like there's an if statement in here. It's a do loop. But actually at the end of this do loop, or at the beginning of this do loop, there's an if statement. It says, if I is less than k, do this loop, else don't do this loop. So these do loops are really have if statements in them as well in their functionality. But of course, it's quite a predictable if statement. So whilst I is anywhere between 1 and k, then this branch always goes the same way. You always go inside this loop. And so this branch prediction hardware can help you with that. It can say, okay, I don't know what I is going to be next, but I know last time it was less than k. So let's assume it is, and let's keep moving, and let's keep filling up that pipeline. And then if it turns out that we were wrong in our branch prediction, then you can always cancel some instructions and roll back. But it lets you do those kind of things efficiently the majority of the time. But compilers and hardware is quite bad at dealing with if statements inside loops here, because it can, stress that branch prediction, and it can mean that the optimization has to be quite conservative, and then you just get low efficiency in the things. Now, in this example here, that n is not changing inside the loop. So I could move that if statement entirely outside that loop and actually have 2 separate loops here, depending on whether n is equal to 0 or not. We can do 2 different things. And now you've removed that branch, that if statement, from inside the loop, and potentially let the compiler do more optimization and more performance things. Now, of course, this one is probably the compiler can do this one for you. It can see n doesn't change in that loop. It can probably do that reordering, depending on how complicated the code inside that loop is, but often it can do that. But you'll, in scientific codes, often have much more complicated things like this one here. So if I less than j, and then else do this, but I is changing as we're going around. So this if statement is changing as we go around. And so that's maybe harder for compilers to do. But you as a programmer can say, well, actually, I can just create two loops. One is if I is 1 to j, which is this first bit here. And then the other is if I is equal to j plus 1 to k, which is this second bit here. And you can do that creation for it. So there are things like that where you can, once you've written a correct program and you're happy with it, you can go back and have a look. Are there places where we're not getting good performance, and are there small refactorings I could do which don't particularly damage the program but do give me better compiler optimizations. There are also other things we can look at here, other aspects of your programming language will cost more performance than others, and so use of data types can be one of those. So 32-bit and 64-bit data types can have a difference in terms of performance, particularly when we have vectorization and vector hardware, which modern processors often do, like ARCHER2 definitely does. And so if you can get away with using lower precision, smaller data types like 32-bit, so that'd be a float or a single precision data type, then you can get more instructions through, you can get more performance out of your processor for a lot of functionality. Now, of course, if you need 64-bit precision for your application, that's what you need, and there's nothing you can do about that. But if you can get away with using 32-bit or lower precision, then you can get higher performance. And it's also worth in the code avoiding things like converting between data types. So converting from a long converting from an int to a long, or a long to an int, or float to a double can be expensive operations to do as well. Compilers will often do, so some of the optimizations that compilers can do for you will be things like common sub-expression elimination, CSE. So they will, in this example here, if we look at D equals A plus C, and then E equals A plus B plus C, we can read that and actually go, actually we can say E equals B plus D, because D is just A plus C, and that's what's going on here. And for our application, that might be a good thing to do. So compilers are quite good at seeing these things, except when you get into scenarios like this, where the order of the operations, of the order of a variable combination has changed inside your program, but is still effectively doing the same thing. And also, it finds it hard to do this common sub-expression removal for things like where you return value for a function, because it doesn't know what a function, if it's running in this black box mode where it's not comparing, it's not looking across all the code, it doesn't know what that function is doing. So it doesn't know whether this function will produce the same output if you run it twice or not. Whereas you as a programmer maybe do know, well, if I run this function and pass it C, it will always get the same value. So I only need to do that once. So common sub-expression elimination is saying, well, we've done this calculation once, we've stored it, we don't need to calculate it again, so we can get rid of that cost by doing that kind of thing. And likewise, we've run this function once, it's not going to change its value, we don't need to run it twice. Compilers can be quite good at it, but there are some times where they fall down, and so looking out for those can be useful. So the function call one particularly is challenging for the compiler, but you can tell the compiler things like the intent variables, or if it's a pure function in Fortran, we'll let it reason more about whether that function call will produce the same result twice. In C, you can have things like const functions and const arguments to the function, which will tell the compiler that things aren't going to change if you run it twice. Compilers will also try and efficiently use the hardware and the processor. So try and use the registers where data is stored efficiently and reuse them so that you're not running out of space when your application is running. and not getting those pipeline stalls which we talked about. And most of the time it can do a good job, but there are some times where it struggles. So particularly things like you've got loops. So we iterate in a loop, but with large numbers of variables that are created inside that loop, or array elements with complex indexes. So you're doing some indirect addressing, and those can make it hard for the compiler to spot places it can free up registers or reuse registers. And so you can help by making temporary variables and then assigning specific things to variables, and then that gives the compiler a bit more chance to reorder register use as well. So here's an example. We've got one of these indirect addressings here where this value is calculated to look up the entry of this value and then stored back here. And this can be hard for the compiler to work out what's going on here, but actually what we can do is, rather than looking up C every time, if we know that this C index is always going to be going up by a factor of 2, for instance, here, we can look up C once, and then each time we can just manually calculate that there. So we've got that calculation here, but that lets us reuse that temp rather than reusing the C as we go around, and that gives the compiler a bit more freedom to move around registers and reuse things. How do you know if you've got some of these kind of problems, what we call register pressure? Well, if you do have register pressure, then the compiler will generate what we call spill code. So that stores a value to memory and then reloads it later on. And so you can actually look in profiling or in assembly and work out how many load stores you expect for a bit of area of code, and then see how many you're actually getting, and that can tell you, okay, maybe we've got some problems there around this kind of thing. Another of the optimizations the compiler will like to do and is pretty good at is loop unrolling. This is a common optimization which means that you get more instructions for the compiler to schedule, so it has more freedom, the hardware has more freedom to move things around and fill up pipelines and do those kind of things. So generally what will happen is the compiler will create bigger copies of things. So we've got an example here. We've got this code down here, this loop here, and then at the end of this loop, each time we go around, we have to update I by 1, and we have to check that I is not less than n, or not greater than n, should I say. And of course, those instructions cost us something. So checking I and updating I cost us something. And also there's limited amount of individual instructions to schedule in here between those branch prediction operations there. Whereas what we can do is unroll this loop. It's doing exactly the same thing, but actually it's doing 4 iterations of the loop in one here. We've made the loop longer. Every time we go around, we increment I by 4. And then here we've got 1, 2, 3, 4 of these before we have to update I and check if I is less than n. Now, of course, we have to be a bit careful about this, because this only works if n divides exactly by 4. Otherwise, something will go wrong here and we'll go off the end of our array. So here they have taken n off, 3 off n, to make sure that we never go off the end of the array. And then they have a loop at the end here which just tidies up the last number of iterations that didn't fit in that loop unrolling. Now again, this is not something we'd want you to do to your code manually most of the time, because it's a bit nasty. You've now got quite specific code which is fixed to 4, an unrolling of 4, and more chance to get bugs in here and those kind of things. But the compiler is pretty good at doing this for you. So you want the loop unrolling for the compiler to do it. You can help it. It wants to only unroll loops where there are independent instructions, where one iteration of a loop doesn't depend on the next, and sometimes it can't tell that. So you can pass in compiler flags or directives which say actually this is an independent loop, even if you don't think it is, and you tell it that so you have more chance to unroll it. You can play around with how much it unrolls it by. So there are compiler flags to tell it to unroll it by 2 or by 4 or by 8 or by 16 to see if that gives you a performance difference for your code. And it won't do unrolling if you've got sort of complex operations inside that loop. So if you have, if statements and those kind of things. So refactoring that code out and making the loop simpler can help this kind of optimization as well. The compiler will also often do, can also do unrolling of the outside loop instead of the inside loop, which can be useful. Particularly if that has impacts on memory locality. So here we've got this I and J. Inside loop is the J loop. In Fortran, in memory, this I index is the most contiguous in memory. So that's the one we want to do there. Want to go over the quickest. We want to iterate over the quickest. And so actually what we do here is instead of unrolling the inner loop, you can unroll the outer loop. And so you're iterating over the I for each J you're having to load up. And that can be a beneficial way of doing these things. Again, the compiler should do this, but it can be something you can help it with. And then there are other things the compiler can do. So the compiler will do things like variable expansion, register renaming, software pipelining, these kind of things, and try and do these things for you. They're a bit more complicated. You don't have to worry too much about what they're doing, but there are ways to, the compiler will be looking to sort of break down dependencies between the operations it have been doing and give itself more freedom, more operations that it can reschedule and rename and move around and those kind of things. And that can, be some of these things. And again, probably not things you want to do by hand, but you can have a look at the compiler and the compiler outputs and say, am I getting the kind of performance I would like here? If not, what can I do to help the compiler do that? And then, if push comes to shove, you can go and have a look at optimization at that level. So in terms of unrolling and variable expansion and those kind of things, function calls, conditionals, and pointer array aliasing are all things that will stop the compiler doing a good job. Now, we've talked about function calls and conditionals. Complex code inside will mean the compiler will struggle to do anything there. Pointer and array aliasing we've not really looked at, but it's more particularly for C and C++ codes where you're using pointers, where you're using sort of raw memory structures. The compiler can't always tell if two arrays or two variables are distinct and point to separate areas of memory, or there's some overlap between them. And in that scenario, it can't really do unrolling or aggressive optimizations because it's not sure if it will impact the correctness of the results by overwriting memory that was going to be used in the next iteration or something like that. There are ways to fix that. So here's an indirect addressing index for a C program. A is being updated on the left here, A is being used on the right here. The compiler doesn't know what index of I is, so it doesn't know that for the next iteration of a loop, it's not going to mess up this result if it does, multiple iterations at the same time, or if it unrolls it. So it doesn't know that A of index I and A of IP don't overlap. And there are ways around this, so you can use a compiler hint to say that, index is maybe connected to I in a particular way. You can tell the compiler it's okay to unroll, or you can rewrite this and you can take that A out of the right-hand side, turn it into a temporary variable, because it's not changing as we go around the loop. And that gets rid of that problem for the compiler here. Now, again, as with all these optimizations, it's not something you should do initially. It's not something you should be doing when you're writing and debugging your code. But once you've got to a point where you want to improve performance, if you want to look at taking the performance of correct code and making it better, these are the kind of things that you can do. The compiler will also potentially do inlining, and so this is taking small functions and putting them in where they're called. because that can reduce the overhead of a function call, which costs us something in terms of performance. You could do this by hand, by yourself, but that makes very bad, hard to maintain code. So ideally the compiler does it for you. And so there are compiler flags which can help it do that for you. Then finally, some of these things, often the compiler is quite limited in what it can do in the end. So it'll perform a number of optimizations, but it can't keep optimizing and keep optimizing. It'll only do a fixed number of optimizations. So some of the reasons you may want to hand implement some of these things like loop unrolling or something like that is to help the compiler do future optimization. So there can be some scope where you want to go in and do a little bit of tweaking of the code, just so the compiler doesn't have to do that particular optimization, but can apply another one instead. Okay, so we've talked a lot about this, but what are the kind of sensible compiler options for ARCHER2? Well, if you're going to use the Cray Fortran compilers, then there's these optimization levels with things to control, number of things to inline, optimization. These H-list ones here will produce you all that info about what the compiler's doing, and then there's parallelization things you can do. And for the Fortran compiler, you generally, it's the default level of optimization, if you don't specify anything, is optimization level 2. And then you can get more aggressive by using things like this. But it's in general, you don't want to go too high on the Cray compiler. On the C compiler, it looks very similar, but it's got O3, OFAST, and then FLTO. This is a bit more of an interprocedural optimization where it can look across multiple files at the same time and do more things there. There are things like save loop mark, which give you the information and parallelization options as well. And for the Cray C compiler or C++ compilers, you think maybe start as O3 in the optimization level, but if you want to go more aggressive than that, there's minus OFAST, minus FLTO as well. And then there's the compilers and the AMD compilers. One of the big differences with GNU is like these GCC, G Fortran, G++. We saw there's lots and lots of compiler flags there. But actually, by default, we don't tend to turn on much optimization if you don't specify anything. So there may be minus O0 or minus O1. And so you probably, once you're ready, want to turn on minus O3 for the GNU compilers. The AMD compilers, I've not shown you those, but they're also available. And they're a bit more like the Cray ones, so they're probably relatively good out of the box. You don't have to do very much there. Okay, so there's a lot of detail there. I appreciate there's a lot of detail there, and a lot, particularly if you're not programming all the time and not using compilers all the time, a lot to take in. And the main things to take away here is the compiler is your tool, and it has lots of functionality that can help you improve performance and check correctness. And that's the first place to start. When you come onto a system like ARCHER2 and you've got a code and you want to make sure you're getting the best performance, start with a compiler, start doing those optimizations through flags and through choices. And then if you need to go beyond that, you can start looking at the code and start saying, okay, which bits of the code is a compiler not optimizing? Why is that? What can I do to help that? Always remembering that we need to do testing. We need to have a good test suite which tracks correctness whilst we're doing this, so we're not breaking the code. And for any of these kind of things, we want to follow that profiling and measuring and then optimizing approach. So we don't want to just go in blind and try and make changes. We want to make sure we're using the best compiler flags that give us the best performance, then profile and look at the code itself and see where the performance is being spent, then focusing on the bits of the code where they're very expensive in terms of runtime, and then look at optimizing there, look at the compiler reports and those kind of things. Okay, you've heard a lot of me speaking. Any questions on that one? what I will do now, well, there's two things now. So there is, let me share my screen again. So we have practical notes here. So this is in the single node optimization course, practical notes under the exercise. So if we go into this thing here, it's going to take its time. If you go into exercises, and then we go into practical notes, you will see it tells you how to get onto the system. You may need to change this TA177. I can't remember exactly what your project number is for this one, but it's yeah, TA213, I think, is the one for this one. And then there is some exercises which I believe you're not quite onto yet, but there is exercises to look at placement and look at what performance looks like if you change where things run on the system. There is one to look at the profiler on ARCHER2. So we've got a CRAPAT profiler with a bit more detail and information here in this handout, which tells you how to use that. And then there is also, for today, the next thing to do is there is this compiler exercise here, where you can play around with the compiler, use the different flags, look at the loop unroll and look at the cache usage and see how choosing different compiler options can change your performance. And so that's we expect you to look at today. So have a look at these three exercises and see how you get on. Any questions on those? And if there's no questions on those, I will just say, let me stop sharing and share again. So just so we wrap up this bit here, and then you can go off and do the practical stuff in your to your heart's content. I'll be around, but you can go and do it in your own time and pace. Just to summarize from today, there was a lot of material, but there's lots of complexity in the computers we use. This is good though, because most of this works for us and most of it works for optimizing our applications. For single node performance, the hardware is key, so using processors and caches and memory effectively is very important. But the compiler is your friend, as we've just heard for the last hour. Compiler is your friend. You use it as a starting point and then start zeroing in on where you want to optimize your code by using compiler reports and the profiler. And then you can look at more advanced things like we'll talk about tomorrow, like OpenMP shape optimizations, memory optimizations, and vectorization. And that's what we'll focus a bit more on tomorrow. Okay, so I will leave it there for the chat-in. As I say, if you have any questions, just let me know. I am here. Otherwise, feel free to jump in on the practicals, on the system, and get going, and then drop back in here when you have, or ask questions in here when you encounter things you don't understand or things don't work, etc., etc.